Welcome everybody. So this week we're going to be talking about the axiom of choice. We were talking about cardinals and we are still in the middle of the cardinals, but to be able to move forward we need some results that really use the axiom of choice. So it's a good point to kind of stop and look at the axiom of choice more deeply. So we have seen a couple of statements so far for the axiom of choice, which we showed there were equivalent. And now we're going to see a few more. So here are all the statements we're going to see. We're actually going to see 6 statements for the axiom of choice, and we're going to prove now that most of them are equivalent, and then we're going to leave a few for later. Okay, so the first one is axiom of choice form 1 that we saw towards the beginning of the course, that says that if you have a relation, then there's a function with the same domain, which is a subset of the relation, right? And you guys remember the picture. We have a relation from one set to another, well, the domain to the range, and in the relation, points are connected to points, but one point might be connected to many other points. In a function, a point from the domain can be connected to almost one point from the range. So for instance, this point is connected to 3 points in the range, and that's not good. If you want a function, you cannot have a function to map one thing to many things. You can only map it to one. So this version of the axiom of choice tells you that there is a subset, a subrelation, which chooses one of the images for each point. So for instance, for this one, it has to choose, let's say, that one. It could be either. For this one, it can be choose that one. For this one, that one. And now every point in the domain is still in the domain of the function. Not every point in the range is in the range of the function. That doesn't matter. The function is a subset, and now we have a function. Okay, so that's form 1 of the axiom of choice. Form 2 is the one that we saw also before about infinite Cartesian products. So what it says here, let's rewrite this. You're given your set I of indices, and for each I we have a set. For each element of I, we have a set. Right? So if this one is I, then here is h of I. Right? And now, what this axiom is saying is that the Cartesian product of the hi's is not empty. So then, in other words, this is saying that there exists a function f with domain I and with the property that f of I belongs to h of I. So the domain of the function is all these points right here, and for each point it chooses one point in h of I. The Cartesian product right here was defined to be the set of all these functions, all the functions whose domain is I, and they go at each point on the right set. The definition of the Cartesian product is fine. What the axiom is saying is that this Cartesian product is not empty, so that there is at least one function with domain I in that property. Okay, so actually there are going to be many. Once you have one, you can prove that there are lots, but just to choose one, it requires the axiom of choice. Third form of the axiom of choice, which we actually used in one of the lemmas, it says that if you have a set A, you can define a map, capital F, that what it does is whenever you take a non-empty set, subset of A, so remember this set up here is a set of non-empty subsets of A, the function is going to give you an element of A. So you input a subset and it outputs an element with the property that the element that it outputs belongs to the set. So it's going to be inside here. Okay, so whenever you choose another set, C here is going to be f of C. And whenever you choose another set D, f of D might be anywhere inside, somewhere there. Of course, you need to take non-empty sets because you cannot choose an element of the empty set. But for all the other ones, you can pick an element inside. Okay, so that's the other form. Whenever you have a subset, just choose an element within that set. And the way you use it usually is you can consider, you can put like whatever, all the sets you're working with, just consider, like put them all in a single set, and then take all that, such that those are the subsets, and then for every set we can pick an element inside. For number 4, it says that if we have a collection A of non-empty sets of disjoint. So it's what is called, well, if you take the union of all A, this is a partition, they're all disjoint. And what it says is that you can find this set C, which picks one element from each. Okay, so for each element A of the collection capital A, so like let's say this one is A, C consists of all the little dots, all the red dots. This is the only one that belongs to both little a, Roman A, and C, right? So for each one you choose, it intersects each of the elements of the partition only once. That's for number 4. 5 is the one we saw last week, which says that if you're having two sets, one has to be, there must be a one-to-one embedding, one-to-one map from one to the other, or from the other one to the one. One way or another, there has to be a one-to-one map, right? And this is what allows us to conclude that between any two cardinals, that if you're giving two cardinals, one has to be less than or equal to the other one. They cannot be incomparable. They have to be comparable in sizes. And the last is the Zorn lemma. The Zorn lemma, that also we saw last week, says that if you are given a collection of sets, and by that I mean just a set of sets, and by that I mean a set. Everything is a set of sets, because everything is a set in our world of set theory. And it satisfies the property that whenever you have a chain included in it, the union of the chain also belongs to the collection. Okay, so remember, a chain is a subset such that all the elements inside are comparable under inclusion. So B is a chain if whenever you take two elements from it, one must be included in the other as a set. Okay, so the hypothesis is that whenever you have a chain that is a subset of your collection, if you take the union of all these nested sets, they're all nested, they're all included in each other. So the union is kind of like a supreme thing, no? They're all included in each other. Take the union, then that one is also in your collection, right? So the collection is a property of your collection, being closed under this union. So you can think of it as kind of being closed under limits, because it's these kind of unions are, if you have a collection of sets that are growing, the union is kind of like the supremum in a sense of these things, right? And what the property of the collection is that whenever you have such an increasing union, which you may think of them as a converging sequence, the limit also belongs to the collection, right? So the collection is closed under taking these supremums of chains. Then you can conclude that it has a maximal element. It's an element of the collection that has no elements greater than it in the collection. It's a maximal within the collection. Okay, so these are the 6 formulations for the axiom of choice, and let's start looking at how is that they imply each other. So let's start proving that 1 implies 2. So here I wrote 1 and 2 again. We did this already, but we can do it again. So in this one, you have to show, so we want to prove 2. So that means we have to start assuming we are given such a function h that like this one right here. So we are given a function h like this one, and we have to now somewhat use number 1 to build such a function f, right? So this, because this part 2 says that exists such a function, we have to use that number 1 to build such a function. And if you look at number 1, it's already about functions existing. So I guess we just have to create the right setting so we can apply 1. So that means we need to create the setting for 1, so that means we have to define a relation to which we can apply number 1. So we consider the relation that consists of all the i's, comma, h, such that h belongs to hi. Okay, so that is a set of pairs, so it is a relation, and the domain is I. Now use 1 to get a function f, including the relation, with domain of f equals domain of R, which is I. And notice that, so what do we have? For each in I, we know that the pair I comma f of I, which belongs to f, that's actually the definition of f, not the set of pairs. The graph is a subset of R, so if since I comma f of I belongs to R, we have that f of I belongs to h of I. That is because these are here. Okay, so that's how we define the relation. We only put the pairs such that the second one, the second component belongs to h of I, where I is the first component. So you must have this. So this is h. F is the one that we wanted. So f belongs to the Cartesian product of h of I, and that's why it's not empty. Good. Let's now prove that 2, the one about the Cartesian product, implies 4, which says that for every non-empty set A, which is a collection of sets that are disjoint, you can find a set that intersects each element of the collection exactly once. Okay? How would you guys think of doing that? Let's draw the picture again. Well, here is the picture. This is what we have. So we're given a collection A of disjoint sets like that. I guess the thing that is drawn here is the union of A, and the union of A is being partitioned by the elements of A. And we want to pick one from each. And what we're given is that the Cartesian products are never empty. So somewhat we have to build this. What is a function h that we want to apply part 2, so that the fact that the Cartesian products are not empty is going to give us the elements that we want. So let A be as in 4. We want to define that. So what is the function h that we are going to define? Essentially, here is the trick. Be the identity. So we let h be the identity of A. Okay. So what do we mean by this? So domain of h is A itself, right? That's the identity of A. So that's the domain. So those are our indices, and for every A in A, h of A is just A, which is a set. Okay, so if you input, for instance, this red set A right here, h is going to output the red set A. Okay, so to be able to apply the part 2, we need to know that all the h of i's are not empty, but we know that because these guys are not empty. Okay, so what is that so what is that part 2 gives us? It gives us a function f with domain of f equals I, which in this case is A, and for all A in the index set, f of A has to belong to h of A, this Roman, has to belong to h of A, which is actually equal to A. Okay, so what our function is doing is, for the function takes the set, like the red set here, and picks a point inside. Okay, so for each of these sets in the partition, picks a point inside. What we want for number 4, we don't want a function, we want a set, right? So what is that we take? Well, take C to be the range of this function f. Okay, so this is giving us the points that h is picking. Yeah, and then observe that C intersection A is what? Well, it's exactly H of A. But that is the only point that belongs to the intersection, because H of A belongs to the intersection because it's in the range and it's in A. This is the only point that belongs to the intersection. On the one side, it belongs to A, and it belongs to C because it's in the range. And there is no other point in the intersection because all the other points in the range, they come from a different set of the partition, and they are all outside A, right? So if you take another set B, its image is going to be not in A because they are all disjoint. That's where we use the fact that they are disjoint to make sure they intersect on one. If they weren't disjoint, we might not be able to make sure they intersect exactly on one point because maybe they are one inside the other and it gets complicated. Okay, so that's how we put 4. Now we want to go back and we want to do that 4 implies 3. Okay, 3 tells us that for every non-empty subset of A, like the B, the C, or the D here, what the function is doing is picking an element of that subset. But now this is for every subset of A, and these guys are pretty much not disjoint, right? We are taking all the subsets of A, and they don't need to be disjoint at all, right? So number 4, though, our assumption though works only for disjoint sets. So we need to figure out how to make our domain of the function a bunch of disjoint sets. And of course it has to be non-empty. So how is that we make these sets not? We need to define our collection of sets A so that we can apply number 4 to. And this is what we're gonna do. We take all the non-empty subsets of A and we do this thing, which is we kind of force them to be disjoint, right? So when we do this thing up here, essentially what we are doing is we are taking the set of all pairs where the first element is the set B and the second element is a member of B. Okay, so if we had our set B up here, we are attaching to each element like a little flag that is B. So this is this new set that we get here is very similar to the set B, except that all of the elements are attached the same, like a little flag. This capital B, which is the name of the set, all of the elements are attached the same thing. So only. But the trick now is that if B and C are subsets of A that are not empty, and they are different, then B cross B intersection C cross C is empty. Because all the elements here, they are pairs, and the first coordinate is B, and all the elements pair, and the first coordinate is C. So they have different pairs. But in this one, if you ignore the first coordinate, we essentially have B, and in this one, if you ignore the first coordinate, we essentially have C. Okay? So now all these sets are disjoint. So now we can apply 4, which intersects each of these in one element. Okay, and now for each element of the collection, we have that C intersects B cross B at exactly one point. Yeah, so that means there is a unique B in B such that the pair B comma B belongs to C. So that is exactly what we want. So now we have a function. Yeah, so that for each B and B maps to a little b in B. Okay, so let F be the set of pairs B comma B such that B belongs to power set of A minus the empty set, and B comma B belongs to C, which is a unique one. That's the image. That's the one that we want. I guess I could have said let's F equals C, because C is already the graph of a function, but actually C might not be the graph of a function because C might have extra stuff. I guess number 4 doesn't say that it doesn't have extra stuff. So here we are removing the extra stuff essentially. But yeah, so C is essentially picking you one element from each set. So we force them to be disjoint, and now the C picks one from each subset, one element. Okay, and finally we need to show to close the circle that is among the first 4 that 3 implies 1. Okay, so now we know that for every set A there is a function that picks an element from each subset, and now we want to get that every relation has a subset that is a function. So we are given a relation R, we want to define F, and we want to figure out what this set A is. Okay, and all we're going to do is we're going to let this to be the range of the relation R. Okay, and now what we're going to do is the following. So little a in R, we want to define f of A, right? But we want it to be such that A comma f of A belongs to the relation, right? So that, right? I mean, that's what we want when we say that the function is a subset of the relation. So in other words, what we want is that A belongs to the set of all the things that are related to A, which we called RA in some earlier video weeks ago. Remember? So what is this guy? This is the set of all the B's that belong to the range of R such that A comma B such that belongs to the relation. Yeah, it's a set of all the things that are related to little I, the A. Okay, so essentially we want to just to pick one element from this set, or from all the possible ones that we can. So there are many possible ones that are related to little a. We want to pick one. So we have our function. So our function before gave us that. Let's call it something else. So let's let h be the function given by 3, sorry. So which picks an element from each subset, and then finally we let f of little a to be the element that h picks of the set A. So among all the possible ones that they can pick, h is going to pick q1. And that's the function that we want. Cool. So what have we done so far? So we started proving that 1 implies 2, and then we proved that 2 implies 4, and then we proved that 4 implies 3, and then that 3 implies 1. So we now have that all those 4 are equivalent. So if you remember last video, we proved that Zorn's lemma implies that all cardinals are comparable, right? That we did that one last week. So what we're going to do today now is to finish and prove that Zorn's lemma implies 1, and therefore the 4 of them all together. And we're going to be missing that the 4 of them together, 1, 2, 3, 4, imply 5. Okay? So we're going to be missing and 6. And we're going to leave that for a few weeks from today when we see ordinals, which are going to give us the tools to prove Zorn's lemma and cardinal comparability. Okay, so let's finish doing 6 implies 1. So we want to do here 6 implies 1. And this one is actually quite simple. So as usual, when we use Zorn's lemma, what we need to do is define the collection A. So let A be the set of all f of functions, and let's apply it correctly. So let f be the set of all the subsets of the relation, and if you want to apply the subset axiom correctly, you have to say belongs to the power set of R. Same thing, but belongs to is the correct way of applying subset axiom, such that f is a function. Okay, so we have all the subsets, and now if you want to be able to all the sub-functions of R. So this is the elements of this collection A are the things that are functions and are subsets of R. Those are the two things we're asking, and we're not asking anything about the domain of R being the domain of F. So we're gonna want to get that from the maximality, from Zorn's lemma, okay? So how are we gonna do that? Well, first, to apply Zorn's lemma, we need to know that we are in the hypothesis. So that if we have a subchain of A, then the union of the chain belongs to A. We showed last week that the union of functions is a function, that the union of a nested, a chain of functions. Right, so we know that the union of a chain of functions is a function, and also if we know, this is very simple, if for every f that belongs to B, f is a subset of R, then the union of all B is also a subset of R. Okay, so now if you have a chain is a subset of A, then the union of B must be a function, and it must also be a subset of R. So the union is going to be also an element of A. Okay, so if you have an increasing collection of functions, it has increasing because it's a chain, increasing collection of functions, which are all included in R, the limit, the supremum, the union, is going to be a function, which is also included in R. So we satisfy the hypothesis of Zorn's lemma, so we can apply it. A has a maximal element, which we can call F. So we know F is a function, F is a subset of R, that's just because it belongs to the collection calligraphic A. And now the last thing we need to show is that the domain of F is the domain of R. How are we going to do that? If domain of F was a proper subset of the domain of R, we could increase the function, right? So let A be an element of the domain of R minus domain of F. Let B, since A is in the domain of R, is connected to something, right? B such that A comma B belongs to R. It has to be something like that. And now if we let F union the pair A comma B will also be a subset of R and will also be a function. It will be a function and a subset of R, so it will be in our collection. And this will contradict the maximality of F. Maximality of F. Okay, because we're adding one more thing to F and we're still in the collection. But since it was maximal, we couldn't add anything. And the fact that it couldn't add anything means that there cannot be it cannot be that the domain of F is larger than the domain of a smaller, strictly smaller domain of R, because otherwise you could put something else. So we must have that if you have a maximal element, the domain of F is equal to the domain of R. And that's how we get that 6 implies 1 and implies all the other ones. Okay, we'll continue in the next video.